So now let me hand over to Alexandra and Julia, and please enjoy the session.
Thank you, Katarina, for a very kind introduction and welcome to our webinar. So let me give you some information about the content. Today, we will talk about environmental friendly wear-resistant coating processes and how we as Atotech MKS understand it. Briefly, we will discuss the differences between electrolytic and electroless processes. Also, we will explore some main coating properties. We will discuss applications and criteria for selection, and last but not least, there will be some takeaways for implementing wear-resistant coatings. Well, let's start with understanding of wear-resistant coating processes. Basically, at Atotech MKS, when we are talking about wear-resistant coatings, we classify them into two types of processes. One type of process is electroless nickel, where again we divide and we distinguish between low phosphorus nickel processes, medium phosphorus nickel processes, and high phosphorus nickel processes. The second type, functional chrome. So in functional chrome today we will talk only about our new hard trivalent coating process, BluCr, because we are on the environmental friendly roadmap, and that's why we want to eliminate possibly all hazardous substances. Well, if we are talking about wear-resistant coatings, of course, it means that they must withstand wear in diverse range of applications. And commonly, the parts, the substrates from the customer, either they are a little bit softer, or they are less wear resistant, or they do not have sufficient corrosion resistant in the environment they are subjected to. That's why basically electroless nickel or functional chrome are the processes to improve the drawbacks of the coating. And last but not least, if used in corrosive environment, wear-resistant coatings, of course, must additionally provide an excellent corrosion protection. And how we do that, we will see in the next slide. And here, short summary: the wear-resistant coating processes you can meet in, I would say, almost each part of the mark. So if we start from automotive, hydraulics, aerospace, heavy machinery, oil and gas, printing, steel mills, and a lot of others. So basically, of course, it's the choice of the customer, but we will advise you which process is better for which application. And saying that, I would hand over to Julia, and during the next session she will explain you the differences between electroplating and electroless process and about some basics and developments. Julia, please.
Thank you, Alexandra. Thank you, Katarina. Hello, everyone, to our workshop. So I will continue with the differences between electroplating and electroless technologies, about the basics and a bit of development. If we have a look at the differences between electroplating and electroless plating technologies, we can see that in case of electroplating, we have in generally a metal anode which dissolves with the current, as the metal cations will be reduced and deposited at the cathode, which is our substrate as well. The coating thickness is dependent on the current density distribution, and we can observe sometimes the dog bone effect. In case of electroless plating, like electroless nickel, for example, we have a metal salt solution, in most cases is nickel sulfate, with a concentration of 100 grams per liter nickel, and we have in our solution also a reducing agent, in our case sodium hypophosphate, and at a certain pH and temperature and in the presence of a catalytically active substrate, the nickel cations will be reduced and the nickel metal will be deposited on the substrate. What we observe here is that the coating thickness is the same all over the part, and this is one of the main advantages of the electroless plating. It's also important to mention that in case of electroplating, we have a pure nickel metal as deposit, while in case of electroless nickel, we obtain a nickel-phosphorus alloy with very good properties. Nevertheless, the electroplating is by far much more cheaper than the electroless technology. At the end, there are two reasons why electroless plating remains relevant. First is the perfect thickness distribution all over the part, also on very complicated shapes, and the improved resistance of the nickel-phosphorus alloy against corrosive environments. Regarding the equipment, what do we need for these two technologies in comparison? We can see that in case of electroless nickel, we don't need anodes, we don't need cooling rectifier, we don't need shielding. But for both technologies, we need to do a replenishment. In case of electroless nickel, this replenishment can be done automatically or manually. In case of hard chrome, blue chrome, we need to do an automatic replenishment. We need to have an exhaustion as well to eliminate the toxic aerosols in the air. We need to have a very accurate pH control in both cases. We need to filter our solution to remove the impurities. And also as heaters, we can use the same heaters, PTFE or ceramic, and the tanks are also similar. Let's have a look at the main coating properties and at the electroless nickel processes at Atotech. First, I would like to give you an overview of the development of the electroless nickel processes, which is actually based on the evolution of the electroless nickel stabilizers used in these processes. So the first generation of the electroless nickel processes was stabilized by lead and cadmium, but as these two toxic heavy metals became banned by the regulations, we were looking for new stabilizers. And so we have developed the second generation of the toxic heavy metal and also toxic heavy metal free generation stabilizers. And these are the 11 compliant processes, the NICAM 11 series, like NICAM 1122, 22, 23, 25. To improve the stability and the coating property of this generation, we developed the third generation where we added an extra non-metallic stabilizer to the system. And so we have developed the NICAM HP 1151, our best sellers in the high P range, the MP 1188, our star in the mid P range, and our most bright mid P process, MP 400. And the last generation of organic and mixed stabilizers with the 11 HP 1050 and HP 1170, with an excellent performance regarding the plating rate, stability, the bath life, and also a very long compressive stress over the bath life. Also, it's very important to mention that this last fourth generation show very good results in terms of corrosion resistance. Depending on the phosphorus incorporation, we have different electroless nickel coating types with different applications. For the low P electroless nickel processes, we have a phosphorus incorporation of 1 to 3 or 2 to 4, and therefore we can use these coatings for different applications like electrical conductivity, soldering, or adhesion and wear with very high hardness as plated. In the range of mid P, We have a phosphorus content of 5 to 9, and we use these coatings for general applications. And with a high P electroless nickel with phosphorus content higher than 10, which can achieve the highest corrosion resistance as plating, they are non-magnetic and they are bendable coatings. So primarily all the electroless nickel coatings are used for engineering application with uniform thickness, quite high hardness and wear resistance, and very good corrosion resistance. The phosphorus incorporation in the coating depends primarily on the process formulation, but by changing the BAT parameters, we can change also a little bit of phosphorus content. So let me give you an overview of the low P range in our portfolio. So we see here the 11LP350, which offers an excellent BAT stability, and the newest NiCam LP300, which offers the lowest phosphorus content in our electroless nickel process range. These processes have a very high hardness as plated. They have a good corrosion protection and solderability. They are suitable for application in alkaline environments, and they have the highest hardness in the product range. As we can see on the right-hand side on the graph, we have compressive stress over the bath life, which is very good regarding adhesion and corrosion protection. We have a high wear resistance and a low sensibility to porosity. And regarding appearance, we have semi-bright to matte coatings. All these processes are compliant with the regulation on the market, ELV, Roche, and WE. In the range of medium phosphorus electroless nickel, which is the most popular technology, electroless nickel technology on the market, these processes are used for general purposes regarding wear and corrosion protection. They have a phosphorus content of 5 to 9. The weaker hardness is about 600 to 700. And it can be increased at 850 to 1050 after heat treatment. In our portfolio, we have our NiCam MP1188 with its variations, NiCam MP-NF for the use of on non-ferrous substrates, and the NiCam MP1189. We have also 11MP603, which is approved for food industry, and our bright MP400. And last but not least, the NiCam MP75, which is our newest product in the mid-P range, which works at a low temperature of 75 in comparison with 88-90 for the other processes. And with the use of this process, we can achieve the same properties by saving a lot of energy. In the high phosphorus range, we have our star NiCam HP1151, which is can be used for general purpose of high P and is suitable for all application. We have 11HP1050, which is our new organic stabilizer system. We have no other metals in the coating apart of nickel. And NiCam HP1170, which is our new process with a very good corrosion resistance. As we can see on the right-hand side, these processes have a better deposition rate in comparison to the previous lead generation, and also much longer compressive stress over the bath life until 6 to 7 MTO compared to 4 to 5 for the lead stabilized high PEN. So all these processes passes nitric acid test more than 30 seconds. We have 10 to 12% phosphorus incorporation in the deposit. We are compressively stressed until 6-7 MTO. We have a very good corrosion resistance using these processes because the coating is pore-free, and we have a very good wear resistance. So while the traditional electroless nickel technology offers EN processes with a limited bath life of 8 to 10 MTO, the use of Eden technology increases the bath life up to 10,000 MTO. Why? Because Eden is an electrodialysis system designed for selectively removing the byproducts like orthophosphate and sulfate from the plating solution, and so we can achieve a steady state plating condition, and we can plate until 10,000 MTO. In our Atotech product range, we offer the whole range of phosphorus incorporation in the coating. So low P electroless nickel for Eden is the product Eden 200, mid P electroless nickel Eden 113. In case of high P, we have Eden 115. Also, it's good to know that by using the Eden technology, we can considerably reduce the waste due to the increased bath life. Now I'll hand over to Alexandra to continue with the BluCr process, with the operation, with the properties and all the features of this new process.
Thank you, Julia. Thank you very much. So now let's talk about electrolytic wear resistant process. And in this case, we will talk about BluCr. So BluCr is the first trivalent based hard chrome process in the market, and we are very proud about that. This process fulfills all the key requirements for hard chrome. The process is stable, offers a long lifetime. The layer offers better corrosion resistance compared to hexavalent chromium process because of the nickel underlayer. We will talk about this during the next slides. Yes, BluCr includes more process steps and requires more involvement if you compare to current hexavalent process. But from the other hand, is completely hazardous substances free and environmental friendly. And last but not least, it has been already used under industrial conditions and is proven by our industrial partners. Well, when we are talking about excellent bath lifetime and hard stability, what do we mean? On the right-hand side, you see the picture. So basically, this is just a picture from the top of our plating tank. You see in the middle cylindrical part, which is cathode, and on both sides you see anode bars with, in this case, graphite anodes. For BluCr process, we use non-soluble anodes. This can be either graphite or it can be MMO, metal mixed oxide coated titanium mesh, or it can be platinized titanium mesh. But important is that we do not need and we do not use anymore any lead substances as in case of hexavalent chrome. And you can see this bluish coloration of the foam on the surface of the bath. And this is basically why our process called BluCr, because of the color of the bath. Yes, on the bottom part of the slide, you can see the parts plated with trivalent chrome. You can clearly see that the deposit is very shiny, it's very bright. We can plate starting from a very low thicknesses from several micrometers for several applications and end up with several hundreds of micrometer or even more. It depends on the applications, but we are able with our process to plate with interruptions, with some grinding steps in between. This is possible. And last but not least, the deposit has macro and micro cracks. And what does it mean? Let's look on the next slide. On the bottom left side, you see the picture. This is the cross section of the steel part plated with nickel layer and blue chrome layer on top. You can see that the nickel layer in this case acts as barrier layer. So in case of corrosive surrounding, you see that the layer is dense, it has no cracks, no pores, and this nickel basically is the reason why the corrosion protection, corrosion resistance is very high. And at the same time, you can see that the blue chrome layer on top of the nickel, it has macro cracks which are going through the whole layer, and you see micro cracks which do not go through the whole layer. And this is why we say, well, the blue chrome, yes, it has macro and micro cracks. You can see basically if you are plating high thicknesses, this is very common for each electrolytic process, also for Electroless, that with higher thickness, the roughness will increase. And a lot of customers perform grinding step either to achieve the final thickness of the deposit or to have a nice smooth surface. And this is basically what is also possible with blue chrome without any problems. You can decrease roughness by grinding after plating. Let's look at the parameters. So during plating, we have mainly two parameters we can play with to achieve different plating rate. So the biggest difference, one of the biggest differences, let's say, for electrolytic hard chrome coating technology, if you compare to Electroless, that the bath is very fast. So the plating rate is fast. And we can achieve plating rates starting from half of the micrometer per minute and end up with several micrometers per minute, which is comparable, for example, to existing Dynachrome technology, who is knowing about that. So this is our hexavalent fast plating technology. And well, in case of blue chrome, this is the same as for hexavalent chrome. To achieve high plating rate and having the same at the same time having very smooth and nice surface, we need to increase temperature. So going for higher current densities, we need to increase also the temperature. About coating, so the coating itself differs from, for example, hexavalent, that the coating has a considerable amount of carbon. And this carbon builds some chromium carbide phases during annealing at higher temperatures. And because of that, the blue chrome coating has extreme resistance in high chloride containing surroundings. It stands several times longer as if compared to hexavalent. So the coating, the chrome coating itself does not corrode under these severe conditions. Few words, well, at the same time, you can see on the bottom left, the blue chrome coating has amorphous structure, it's non-crystalline, and the hardness varies as plated from 800 to 1000, but it can be increased over 1000. We will see on the next slide. Well, here on the right hand side, you can see a graph. The green dots represent the hardness evolution with increasing of the treatment temperature, post-treatment temperature. And the blue squares represent the Tabor wear index. You can easily see that the hardness increases almost linearly over the heat treatment temperatures, and we can achieve up to 2000 Vicas at 600 degrees C heat treatment for 2 hours. At the same time, Tabor wear varies a little bit, but it decreases also at extreme temperatures, and this is, as I said, due to the formation of the chromium carbide phases. On the bottom side of the slide, you can see several cross sections. So basically, these are the blue chrome layers plated on nickel on steel and subjected to different post-heat treatment temperatures. You can easily see that the crack structure change a little bit. So some micro cracks appears at very high temperatures, and also the crack width increases, which can be beneficial for some application, like for example surroundings where the part are in the oil surroundings, so the oil coming into these cracks, and doing that prolongs the wear time of the part. If we are talking about applications of blue chrome trivalent hard technology, well, as I said, very commonly for technical machinery, for hydraulic part, any heavy part, for standard automotive technology, a lot of applications. Also for any general application, you can use hard chrome. And last but not least, as I said, in extreme high chloride containing environments, blue chrome is very, very welcome and resistant. And for the next slide, I will hand over to Julia, and she will give some insights about applications of Electroless nickel technology.
Yes, so I will continue with the application of our Electroless nickel processes. As you can see on the right-hand side on the cake diagram, the main application field of Electroless nickel consists of corrosion protection application, followed by wear and hardness, also because of the lubricity and the magnetic property. We can use Electroless nickel in several applications. And all these properties are combined with, as I mentioned before, with the perfect uniformity of the deposit. That's why we can find Electroless nickel on large interior surfaces, on substrates with very complicated shapes, on inner surface of pumps, dryers, tube, gasoline, or chemical substances because of the high corrosion resistance. Also on printed circuits, boards, and electronics industries for corrosion resistance and solderability. And also what is good to know is that the deposit thickness plays also a major role for the application. At a very, very low thickness, we can use Electroless nickel as a diffusion barrier, as undercoat for electrical conductivity, for wear, and a bit of a bit of corrosion protection. If we increase the deposition thickness, we can use Electroless nickel, for example, in non-marine outdoor exposure with a moderate wear at 25 micrometer, and for very harsh conditions with exposure to acid solutions, at sulfur dioxide, oil and gas, in oil and gas industry, elevated temperature and pressures, we need a higher deposition thickness, like 75, 80, 100 micrometer. Now I hand over again to Alexandra to continue with the criteria for choosing one or the other technology, and to summarize the presentation.
Okay, let's come into the last slides, and here we prepare a summary for you where we tried to put the main properties and the main differences between four type of processes: low phosphorus EN, medium phosphorus, high phosphorus, and hard chrome. Well, you can see that there are some differences, there are some similarities. So when coming to the selection criteria, which process do you need for your specific application? Of course, you need to know at the end the very clear requirements. Is it the uniformity of your part? Then maybe of the thickness of the layer, then maybe you need to go for electroless nickel. But is the part subjected to very, very extreme wear conditions? Then maybe you will have no chance and need to use hard chrome. Or maybe in some cases you need the combination of both. All these questions you can put to us, and we are for you there, and we will advise you what is the best combination or which process will be more suitable for your applications. And saying that, I will move to our last slide for some takeaways for you. Wear-resistant processes. We talked today about BluCr, trivalent hard chrome process, and several portfolio of electroless nickel processes. For some applications, well, the technologies are different. If we are talking about electroless and electrolytic, sometimes we need different equipment and some different operations, and we need, of course, different chemistry. But important is to know that in a lot of cases, the properties are very similar, and it allows similar applications. And also the choosing criteria, of course, derives from the requirements of your parts at the end. So thank you very much for your kindly attention, and let's start the Q&A session. Thank you.
Thank you very much, Julia and Alexandra, for the great presentation. And as you said, we will now proceed with our Q&A session. I would like to remind you again that we will cover as many questions as possible during our Q&A session, and all the rest will be answered by Julia and Alexandra after the webinar via email. So I would say let's start with the first question. What is the variation in thickness with EN process when plating rack versus barrel?
Yes, I can answer this question since it's a matter of electroless nickel. So with electroless nickel, as I explained, we don't need any current. We will not have any thickness variation. And ideally, we don't have any thickness variation between rack and barrel. Any variation which can be observed is due to other factors like solution dynamics or some temperature variations, pH variations, lack of agitation in the bath after replenishment, and things like this. Thank you.
Thank you very much. Next question is regarding BluCr. Which kind of internal stress has BluCr?
I will take this question. The BluCr has tensile type of internal stress over the whole time, and that is basically why we are also recommend that the nickel undercord we were talking about has also tensile type of internal stress. Why? Because the BluCr has actually, as each chromium process, during the plating or after the plating, the chromium layer tends to release the stress as soon as possible, and this is why in case of BluCr these cracks are forming. So if the if the stress of the sublayer is, for example, too much compressive, or if the ductility is not high enough, the layer can crack also. And in that case, of course, the corrosion protection will not be there. That's why it's very important to think about which nickel is plated under the BluCr, and also what are the final applications, what are the conditions. Thank you for the question.
Thank you. Here's another one. What happens to corrosion resistance after heat treating the parts?
I think this is an Electroless nickel question, and I will try to answer it. So after the heat treatment, Electroless coating sometimes changes and deposit shrinks, especially for high phosphorus coatings, because these coatings are amorphous in structure, and after heat treatment at about 300 degrees for 4 hours or 400 degrees for 1 hour, that the structure changes and crystallites, nickel phosphate crystallites will appear. This change the structure, and then this lead to a shrinkage of the coating volume, and this will induce a high stress in the coating. This will cause micro cracking in the structure, and this will provide potential failures, potential sites for maybe for the direct access to the substrate, or of course it will it can be seen as a damage of the corrosion and the decrease of the corrosion protection of the coating.
Thank you very much.
Corrosion protection will decrease after heat treatment.
Thank you, Julia. We have a similar question, but I think this time it's regarding in regards to BluCr. Why is hardness increased during the heat treatment, but in regards to BluCr then?
Yeah. Okay. So, well, as I mentioned already, the hardness, the BluCr layer itself, chromium layer, contains this carbon, and the carbon will build up this chromium carbide phases. There are a lot of different phases, and depending on the temperature you apply, let's say starting from 150, 200 degrees C, very slowly also the properties of the layer will change. The hardness will increase, the wear will increase, and this is exactly due to these chromium carbide phases which build up at the high temperature. And maybe let me a very short comment on Julia's answer also. What happened with corrosion protection for BluCr, for example, then during heat treatment? Again, it depends on the nickel. So this will be, for example, the case as Julia already explained. If you apply Electroless nickel, if you apply electrolytic nickel coatings, very, very important is also the ductility, because if the cracks become wider in BluCr, the nickel layer underneath needs to resist that and to build up the stress without cracking. Yeah, thank you.
Thank you. Let me have a look. Next question. Why does a high PEN coating achieve the highest corrosion protection in the salt spray test?
Yes, I will pick this question. This is because the high P coatings have on the one side they have the lowest deposition rate, so the coating process is the slowest, and then the coating is building not very fast, and then we have the lowest porosity. So we have the highest corrosion protection with the high P coatings. And with these coatings, we have the lowest amount of defects. So it's the best coating for corrosion protection.
Thank you very much. Next question. This is an interesting one, actually, because we all know about this issue. Currently, there's a big pressure regarding usage of PFOS and PFAS containing substances and use, for example, in mist suppressants. What is about mist suppressant for BluCr or EN?
Let me answer the question. Yes, this very interesting and actual question. So basically, if we are talking about mist suppressants, well, during the hydrogen evolution, we know that this is the concurrent cathodic reaction during plating, and some electrolyte droplets basically will be taken out with hydrogen, and what we will see so-called spray misting. And this leads, of course, to air pollution with aerosols containing these electrolyte chemicals. And because of that reasons, exhausts and mist suppressants are usually used. And we are very proud about that. As I said, we do not use any hazardous substances for BluCr process. So the mist suppressant we used as well doesn't contain any PFOS or PFAS or any fluorinated compounds. And saying that, maybe be attentive in the next months. I guess we will have a webinar for this topic, especially how active we are in replacing of these substances at Atotech. Thank you.
Thank you very much, Alexandra. I think this was a perfect end to our Q&A session. And we would like to thank you again, our presenters, for the great presentation. And also thank you, everyone. We really appreciate you being here today.